I want you to imagine something for a second. You're standing out on this sun-baked tarmac.
Okay, painting a picture here.
Yeah. And sitting on the concrete just a few feet in front of you is a multi-million-dollar piece of high-tech machinery. It's this highly sophisticated unmanned aerial vehicle.
Right, a serious military or industrial drone.
Exactly. We're talking about a drone packed with, cutting-edge optical sensors, advanced propulsion, and just enough onboard processing power to run a small city. It represents years of research and millions in funding.
And it's designed to fly hundreds of miles into really complex environments to execute these critical missions.
Right. So imagine this absolute marvel of modern engineering lifting off, looking incredibly majestic,
Yeah.
and then it just instantly falls out of the sky like a brick.
Ouch. Yeah, that is the nightmare scenario.
And why did it crash? Well, because an hour earlier, a technician happened to brush against its carbon fiber chassis while wearing a static-charged wool sweater.
Oh, wow, yeah.
Or, maybe during the flight, a single microscopic drop of rain managed to find its way into a fraction of a millimeter gap in the casing and just short-circuited one critical wire.
It sounds completely absurd, but honestly, that is the razor-thin line between a successful deployment and a total catastrophic failure.
Which is exactly what we're going to explore today. We are going on a deep dive to uncover this invisible, brutal, and frankly mind-boggling gauntlet of engineering standards that these drones absolutely have to survive.
And they have to survive all of this before their landing gear ever even leaves the ground.
Exactly. We are talking about simulating the absolute worst conditions that Earth, and humans for that matter, can throw at a machine.
It's an incredibly hostile environment up there.
It really is. So to do this, we've pulled together a massive stack of source material for this deep dive. We're looking at really dense military testing specifications.
Yeah, specifically the legendary MIL-STD-810H for environmental torture and MIL-STD-461G for electromagnetic warfare.
Right. And we're also parsing through NATO's strict airworthiness standards, plus some very recent cutting-edge engineering test reports detailing extreme fault injection.
Which is a fancy way of saying they try to break the software on purpose.
Yeah, exactly. So the goal of this deep dive is to shortcut all those thousands of pages of engineering data just to show you exactly what it takes to build a machine that outright refuses to die.
What's fascinating here is that if you actually read through the evolution of these military and NATO standards, particularly the transition to the newer H revision of MIL-STD-810, you see a fundamental paradigm shift.
A shift in how we build things.
A shift in how humanity approaches engineering as a whole, really. Historically, engineers just used these generic one-size-fits-all checklists.
Like just bake it in an oven for an hour and see if it melts.
Pretty much. You'd look at a table and it would say, test your electronics to 50 degrees Celsius, and you did it, check the box, and moved on.
I'm guessing they don't do that anymore?
No, the modern industry has completely abandoned that. They've moved to highly tailored approaches, creating what the documentation actually calls life cycle environmental profiles.
Life cycle environmental profiles. That sounds intense.
It is. It means engineers have to meticulously chart out every single minute of a drone's expected lifespan. Then they design tests that perfectly simulate the bespoke nightmare scenarios that one specific drone will face.
So they don't just test for generic heat anymore.
Right. They test for the exact thermal shock of a drone moving from, say, an air-conditioned hangar in the desert directly out into 120-degree direct sunlight. It is entirely custom-tailored torture.
Okay, I'm picturing an engineer in a lab coat acting like a very sadistic tailor.
That's honestly not far off.
But before they can even begin this bespoke physical torture, there's a whole preliminary phase. Because if I'm reading these test reports correctly, the very first stage of trying to destroy the drone doesn't even happen in the physical world.
No, it starts long before that.
Right. It happens before a single sheet of carbon fiber is laid up, and long before a motor is ever mounted. They start in what I'm calling the virtual crucible.
The simulation phase. And it is arguably the most critical bottleneck in the whole process. This is the realm of the digital twin.
Digital twin. So they're building the drone in a computer first.
Exactly. It has revolutionized modern reliability testing. You construct a mathematically perfect digital replica of your drone to see how the brain reacts before it ever has a physical body.
The documentation mentions S-aisle and H-aisle testing as the core of this phase. That stands for software in the loop and hardware in the loop, right?
You got it.
So break down what that actually looks like in a modern engineering lab.
Okay, let's start with software in the loop, or SIL. Imagine you are writing the core intelligence of the drone, which is the flight control software.
And a popular one mentioned in our sources is the PX4 autopilot system, yeah.
All right, PX4 is very common. So you are constantly writing new experimental code to make the drone fly better, but you absolutely do not want to test unproven code on a heavy physical machine.
Because it has spinning blades that could crash into a building or, hurt someone?
Exactly. So you keep it purely digital. You take that PX4 flight control software and you run it on a standard desktop computer.
But how does the software know what to do if it's not flying?
Well, you have to trick the software into believing it is actually flying. To do that, engineers connect it to a high-fidelity physics simulator. A really common one they use is called Gazebo.
Gazebo, okay.
Yeah, and they run this entire setup in a sandboxed environment, often using Docker containers on something called ROS2.
Whoa, okay, hold on. We just hit a massive wall of software jargon.
No, let's unpack it.
I know Docker is basically a way to package software so it runs consistently anywhere. But what is ROS2? Why does a drone need a robot operating system?
That is a really great distinction to make. ROS2, the robot operating system, isn't an operating system like Windows or macOS.
Oh, it's not.
No, think of it more as a digital nervous system. A drone has dozens of sensors, right? Cameras, gyroscopes, barometers, and dozens of outputs, like the motors.
Right, lots of moving parts.
ROS2 provides the communication architecture that allows all these different nodes to talk to each other instantly and reliably. So in the SIL setup, you use ROS2 to pipe data between your flight software and your physics simulator.
Oh, I see. So the PX4 software is just sitting there in the computer, totally oblivious, thinking it's a beautiful sunny day.
It genuinely believes it is airborne. The simulator feeds it incredibly complex fake data. It sends a fake GPS coordinate, fake wind resistance based on digital aerodynamics, even fake barometric pressure for altitude.
And then the software reacts to that fake reality.
Exactly. The flight software processes that fake reality and sends out commands saying, spin motor 3 slightly faster to counter the wind.
That's wild.
And then the simulator receives that motor command, calculates the new aerodynamic state of the virtual drone, and sends the updated fake sensor data back to the software. And this loop happens hundreds of times a second.
Okay, so that's software in the loop. What about hardware in the loop, the HIL?
HIL is the logical next step. Instead of running the flight software on your desktop computer, you take the actual physical circuit board, the real microchips that will go into the final drone.
And you plug those into the simulator?
Exactly. You plug that physical board into your computer's simulator. So now you are testing the real physical circuits alongside the software, but still operating safely in a simulated world.
You're literally plugging the physical brain into the matrix.
That's a great way to look at it.
But once it's in the matrix, the engineers seem to turn incredibly hostile. The reports outline a process called fault injection.
Oh, yeah. It is intentional, calculated hostility. Fault injection is the process of deliberately introducing catastrophic, potentially fatal errors into the digital environment.
Just to see if the flight controller's logic can survive them.
Precisely. The sources detail scenarios where engineers will be running the drone in the simulator, perfectly stable, and then they instantly cut the GNSS signal, the GPS, down to absolute zero.
To just totally blind it.
Right. Or they program the simulator to hit the digital drone with an unexpected 50-mile-per-hour crosswind shear. They even go as far as simulating a complete physical lockup of a vertical lift motor.
Wait, like the drone is hovering and suddenly one of its 4 propellers just stops dead?
Yep. They just yank the virtual rug out from under the machine.
That is brutal. And the standard they hold the software to is astonishing. The engineering requirements state that the system must identify the injected fault and automatically switch to a degraded control mode or a safe hover mode within 100 milliseconds.
To put 100 milliseconds into perspective for you, the average human blink takes about 300 to 400 milliseconds.
Oh, wow.
Yeah. So in roughly a third of the time it takes you to blink your eyes, the drone's brain has to register that a motor has died.
And it has to realize it's rapidly tipping upside down, I assume.
Right. It has to mathematically recalculate its entire aerodynamic envelope, adjust the power delivery to the remaining 3 motors to compensate for the massive physical imbalance, and stabilize the aircraft.
All before a human operator even realizes something went wrong on their screen.
Exactly.
But this brings up a logistical question for me. If the goal is to build a tough drone, why spend months playing a video game? Why not just build a bunch of rapid prototypes, take them out to an empty field, and fly them until they break?
You'd think physical testing would be faster, sure. But it comes down to statistics, safety, and the sheer scale of modern aviation standards.
Scale in what way?
Well, if you look at the broader frameworks that influence this, like RTCA DO-160, which is this massive aviation standard governing environmental conditions for airborne equipment, you realize you have to prove statistical reliability.
You can't just prove it works once on a sunny Tuesday.
Right, you have to prove it works 99.999% of the time. And to do that, you have to run thousands, sometimes tens of thousands of test cases.
Okay, yeah. Doing that with physical drones would be a nightmare.
Imagine the time and money required to physically build, crash, rebuild, and recrash 1,000 drones just to find one rare line of bad code. A bug that only triggers, say, during a specific crosswind while the GPS is jammed.
It would bankrupt the engineering firm and take a decade.
Exactly. So the virtual crucible allows them to verify the fail-safe state machine?
The fail-safe state machine. That's basically the core logic tree of how the drone saves itself.
Yes. They can test that logic across millions of permutations without spending a single dime on replacement parts.
Okay, that makes total financial sense. But math is clean, and the real world is, well, it's messy.
Very messy.
Like a computer model of wind might be incredibly complex, but it's still not actual physical air hitting a physical piece of plastic.
Yeah.
There has to be a limit to what the matrix can teach them, right?
The reports we reviewed highlight exactly that limitation. Engineers actually refer to it as the sim-to-real gap.
Sim-to-real gap. Makes sense.
A simulator is ultimately just an approximation of reality, based on the physics equations we feed into it. It often struggles to perfectly capture microscopic, real-world variables.
Like what kind of variables?
For instance, the simulator might not accurately account for the tiny electrical latency inside a physical copper wire as it heats up in the sun, or the incredibly chaotic aerodynamic turbulence that comes off the specific shape of a carbon fiber propeller blade when it bends just slightly under a heavy load.
Because the computer thinks the propeller is perfectly rigid.
Exactly. The sources point out that a set of control parameters, known as PID tuning, might work perfectly in the simulator, keeping the virtual drone rock solid. But when you load that exact same code onto the physical drone,
It all falls apart.
yeah, that tiny, unaccounted for latency causes the physical drone to start oscillating wildly, and it just crashes.
Which explains why the reports mention passing an initial software gate, like completing 50 hours of continuous SITL testing without a single freeze, as just the starting line.
It's just the bare minimum to get out of the lab.
It gives them the confidence to build the actual hardware without it crashing 5 seconds after takeoff. But once they bridge that sim-to-real gap, the real punishment begins. We transition from tracking digital errors to watching actual physical destruction.
Right. This is where we leave the computer lab and walk into the environmental testing facility. This is the domain of MIL STD 810H.
The United States Department of Defense Test Method Standard for Environmental Engineering Considerations. This document is practically a legend in engineering circles.
Oh, absolutely.
It's over 1,000 pages long, and it essentially defines what the word ruggedized actually means on a global scale.
If a manufacturer claims their drone or their radio or their laptop is military grade, this is the gauntlet it had to run. And as we discussed earlier, the H revision is ruthless because it demands that custom tailoring.
So let's crack open this customized torture manual and look at the physics of how they actually try to break things. The very first one that caught my eye is method 500.6.
Ah, low pressure or altitude testing.
Right. The sources talk about throwing the drone into an altitude chamber and simulating a 6,500-meter vacuum. That's roughly 21,000 feet.
It's very high up.
Now, a gasoline engine obviously suffocates without oxygen, but a drone is powered by lithium batteries and electric motors. They don't need to breathe. So why does a lack of air pressure even matter?
It was entirely about heat transfer and the fluid dynamics of our atmosphere. Air isn't just something we breathe. From a mechanical perspective, air is a fluid and it acts as a critical coolant.
Like the radiator fluid in your car, essentially.
Exactly. When a drone is flying near sea level, the air is thick and dense. As the drone flies, that dense air rushes over the electric motors and the circuit boards, absorbing the heat they generate and carrying it away through convection.
Okay, but at 6,500 meters, the air is incredibly thin.
Right. The atmospheric density drops drastically. The sources point out a startling metric. In this simulated near vacuum, the drone loses 40% of its convective heat dissipation capability.
Wait, it loses almost half of its cooling ability just by flying higher.
Yes, exactly. And simultaneously, because the air is so thin, the propellers have to spin significantly faster, drawing more electrical current just to generate the same amount of lift.
Oh, I didn't even think of that. There's less air to push against.
Right. So the motors are working harder, generating more heat. At the exact moment, the environment loses 40% of its ability to cool them down. The test is verifying whether the drone will simply melt its own internal wiring while trying to stay aloft.
That makes perfect sense for the motors on the outside. But the reports also mention a huge danger to the internal sealed components.
Yeah, think about the physical construction of modern electronics. A drone relies on tightly sealed compartments. The lithium-ion battery cells are sealed to prevent moisture from ruining the chemistry.
The capacitors on the circuit boards are sealed too, right?
Yep, and certain barometric sensors are sealed in very specific ways. Now, these components were manufactured and sealed on the factory floor at sea level pressure, roughly 14.7 pounds per square inch.
Okay, so they have sea level air trapped inside them.
Exactly. When you suddenly place them in a 6,500-meter vacuum, the atmospheric pressure pushing inward on those components vanishes.
It's the exact same physics as pulling a deep-sea fish up to the surface too fast.
Oh, that's a good comparison.
Yeah, the pressure inside the fish's body is so much greater than the surface pressure that its stomach actually pushes out of its mouth.
It is a very vivid but highly accurate analogy. The internal pressure of the sealed battery cell is suddenly massively higher than the surrounding environment. The air trapped inside the battery pack desperately wants to expand.
So a 500.6 test is literally checking to see if the sealed battery packs will swell up like balloons.
Swell up, rupture their casings, and violently explode due to that pressure differential. The engineers have to design specialized venting mechanisms or use heavy reinforced casings just to survive the lack of air.
That is wild. It's not just about flying, it's about keeping the drone's internal organs from rupturing. Let's shift from pressure to temperature. The documentation outlines methods 501.7, 502.7, and 503.7. These are high temperature, low temperature, and the most brutal of the three, temperature shock.
Thermal shock is a nightmare for hardware.
The test profile calls for the drone to be plunged from minus 40 degrees Celsius deep freeze temperatures to a blistering plus 57 or even 75 degrees Celsius in less than a single minute.
Most people hear heat test, and they assume the engineers are just checking to see if the plastic chassis melts or if the battery catches fire.
Right, that's what I assumed.
But temperature shock, rapidly oscillating between those extremes, is actually a test of mechanical stress at a microscopic level.
Mechanical stress from temperature.
Yes,
Okay.
because a drone is not a single solid piece of material. It is a highly complex assembly of vastly different elements. You have a rigid carbon fiber frame, you have aluminum mounts holding the motors, you have pure copper wiring, silicon microchips, and various alloys of solder holding the electronics together.
Okay, a lot of different metals and plastics.
And the critical issue is that every single one of those materials possesses a vastly different coefficient of thermal expansion.
So when they get hot, they physically grow in size, but they all grow at completely different speeds.
Precisely. Let's look at the circuit board. You have a silicon microchip soldered to a fiberglass board using a lead-free metal alloy.
Okay.
When you drop that assembly from freezing cold into an oven at 75 degrees Celsius in 60 seconds, the fiberglass board might expand outward rapidly, while the silicon chip sitting on top of it barely expands at all.
Oh, I see. It's like taking a frozen glass cup out of your freezer and instantly pouring boiling water into it.
Yes, exactly.
The glass shatters because the inside layer expands before the outside layer can catch up. The material basically rips itself apart.
And that is exactly what happens on the microscopic level inside the drone. That differential expansion creates immense mechanical shearing stress at the connection points.
So the thermal shock test is specifically looking to induce microscopic fatigue cracking.
It wants to see if the delicate solder joints will physically shear and snap off the board simply because the materials underneath them shifted in different directions. Furthermore, it aggressively tests the conformal coatings.
Okay, I saw that term in the specs. What is a conformal coating?
It's a very thin layer of specialized polymeric film. It's sprayed or painted over the entire completed circuit board. Its job is to protect the exposed metal traces from moisture, dust, and chemical corrosion.
Like a waterproof sealant.
Right. But during severe thermal shock, as the board expands and contracts violently, that conformal coating can become brittle and literally shred or crack, leaving the vital electronics totally exposed to the elements. They will cycle the drone back and forth between these temperature extremes repeatedly, just trying to break the chemistry of those bonds.
Okay, so The battery didn't explode in the vacuum,
Yeah.
and the microchips didn't shear off the board in the oven. But a drone doesn't just sit still, right? It vibrates violently.
Very violently.
Which brings us to method 514.8, the vibration test. Now, obviously, anything with rapidly spinning propellers is going to shake. But the standard specifically demands something called sign-on-random vibration. That sounds incredibly specific.
This specific test highlights just how advanced MIL-STD-810H has become compared to the older methods. If you analyze a drone flying in the real world, it doesn't just experience one type of vibration.
It experiences different types at the same time.
Yes, it experiences two distinct overlapping mechanical forces. First, you have the random vibration. This is the broad, chaotic, unpredictable shaking caused by the wind buffeting the chassis.
Or like the aggressive jostling it takes while bouncing around in the back of an unsprung military transport truck driving down a dirt road.
Exactly. It is a wide spectrum of low-frequency noise.
Just a general chaotic rattling.
Right. But superimposed directly on top of that chaotic rattling is a very clean, incredibly specific, high-frequency rhythmic vibration. That is the sine wave.
And where did that sine wave come from?
That rhythmic vibration is generated by the electric motors and the propellers spinning at maybe 5,000 or 8,000 revolutions per minute.
Oh, that makes sense. It's a constant hum.
So the sign-on-random test takes a massive industrial shaker table and programs it to perfectly mimic the complex, coupled stresses of both the chaotic turbulence and the rhythmic motor hum simultaneously.
But why is mixing them so much worse than testing them separately? Like, why not just shake it randomly and then hum it?
It all comes down to structural resonance. Every physical object has a natural resonant frequency. If the rhythmic sine vibration from the motors happens to align with the natural resonant frequency of the drone's carbon fiber arm.
Let me guess, the arm starts to amplify the shaking until it snaps.
You got it. By layering the sine wave over the chaotic random vibration, you create bizarre harmonic interactions. These interactions can uncover hidden weaknesses in the frame that would never show up in a simple up and down shake test.
That's terrifying.
In fact, 810H introduced method 527 multi-exciter testing. They realized that shaking a drone just up and down, then turning it and shaking it left and right just wasn't realistic. Reality happens in 3 dimensions simultaneously.
So they shake it in all directions at once.
Yeah, they use shaker tables that vibrate the drone on multiple axes at the same time to see if the twisting forces will physically tear the screws out of their threads.
It's like putting it inside a paint mixer that's inside a centrifuge.
That's an intense visual, but pretty accurate.
And if the frame survives the multi-axis paint mixer, they try to drown it and dissolve it. The sources detail methods 506.6 and 504.3. This is rain, dust, and fluid contamination.
Right, the ingress tests.
The test parameters mention blasting the drone with rain at 18 meters per second.
Yeah.
That is literally a tropical storm force gale driving water into the chassis.
The primary goal here is testing the ingress protection, or IP seals. They want to ensure that high-velocity water cannot force its way past the rubber gaskets and into the avionics bay.
Because if it gets in there, it would instantly short out the flight controller we just talked about.
Exactly. But method 504.3 takes it a step further into chemical warfare. Military and industrial drones don't just encounter water, they operate on tarmacs covered in incredibly nasty chemicals.
Like what?
Well, this test intentionally exposes the drone to highly corrosive aviation fluids. We are talking about de-icing chemicals, synthetic jet fuels, and hydraulic fluids like Skydrol, which is notoriously aggressive.
Oh, I've read about Skydrol. If you spill Skydrol on regular plastic, it will practically melt it into a puddle.
It really will. So the engineers can't just use standard rubber gaskets or cheap 3D printed plastics to seal the drone. They have to use specialized fluoropolymers and advanced elastomers.
So the test is making sure the seals don't just disintegrate.
Right. It verifies that when the drone is soaked in these aggressive chemicals, the seals won't swell up, degrade, become brittle, or dissolve. Because a rubber seal that has swollen to twice its size from absorbing jet fuel is no longer maintaining a watertight barrier.
Okay, let's take a breath and look at where we are. Our hypothetical drone has survived the virtual danger room. Its batteries didn't burst in a 6,500-meter vacuum.
Right.
Its circuit boards didn't shatter when rapidly frozen and boiled. The multi-axis vibration didn't rattle its screws loose, and its seals held up against a tropical storm of toxic hydraulic fluid.
It has successfully survived the physical environment.
But our sources make a very clear pivot here. They point out that there's another environment the drone has to survive, one that is entirely invisible but just as deadly. I'm talking about the electromagnetic spectrum.
This is a completely different battlefield. This brings us into the domain of MIL STD 461G.
So why does this standard even exist? Why do we care about invisible energy?
To understand that, you have to realize that the modern airspace, especially around military bases, airports, or industrial centers, is overwhelmingly noisy from an electromagnetic perspective.
Like radio waves and stuff.
Exactly. You have radar dishes sweeping the sky, massive cellular towers blasting out 5G signals, radio arrays from other aircraft. The air is thick with invisible energy. And a drone itself is basically a highly coupled electromechanical chemical network.
Meaning every wire, battery, and microchip is intimately tied together. A surge of electricity in one spot can instantly travel and cause a fire somewhere else.
Precisely. A failure in a single tiny node due to electromagnetic interference, or EMI, can cascade at the speed of light and crash the vehicle.
So how does 461G handle this?
The standard approaches this invisible threat from two different angles: emissions and susceptibility.
Okay, let's break down the emissions side first. The sources cite tests CE102 and RE102, which stand for conducted and radiated emissions. This is essentially testing how much electromagnetic noise the drone is shouting out into the world, right?
Right. Remember how much electrical power is required to lift a heavy drone? The primary culprits here are the electronic speed controllers, the ESCs.
These are the devices that tell the motors how fast to spin.
Yes. And they don't just send a steady stream of power. They use something called pulse width modulation. They rapidly chop the high-voltage electricity into thousands of tiny pulses every second to precisely control the motor's speed.
And chopping that much electricity creates noise.
That violent chopping of high-voltage current generates immense amounts of high-frequency electrical noise.
So the drone is basically its own worst enemy. It's generating a massive magnetic field just by trying to fly.
Exactly. The emissions tests ensure that this internal noise doesn't cause a self-inflicted crash. Conducted emissions ensures that the noise from the motors doesn't bleed back down the copper power lines and scramble the main computer.
And radiated emissions.
That ensures that the motors aren't acting like broadcast antennas, radiating that noise out into the air around the drone.
Why is it so critical to keep the drone electromagnetically quiet, though? Does it really matter if it's broadcasting a little noise?
It matters immensely because the drone relies on incredibly weak, hypersensitive external signals just to know where it is. The most critical is the GPS or GNSS signal.
Right, from satellites.
Think about where that signal comes from. It is transmitted from a satellite orbiting 12,000 miles away in medium Earth orbit. By the time that signal passes through the atmosphere and reaches the tiny antenna on the drone, it is astonishingly faint.
Barely a whisper of electromagnetic energy.
If the drone's own high-voltage motors are screaming electromagnetically, they will completely drown out that faint GPS whisper. The drone will effectively blind itself, lose its positioning data, and likely trigger a failsafe or fly away.
That is a phenomenal way to picture it. It's like you are standing in a room trying to hear someone whispering a crucial secret to you from 100 feet away.
Right.
That whisper is the GPS signal. But you have a blaring air horn duct taped to your own ear, which is the electromagnetic noise of your own motors. You absolutely have to silence the air horn to have any hope of hearing the whisper.
It's a constant battle for signal clarity. But it gets even more complex when we flip the standard and look at the susceptibility tests, specifically CS114 and RS103.
Okay, so if emissions was about silencing the drone's own air horn, susceptibility is about what happens when the outside world starts screaming at the drone.
Exactly. Conducted and radiated susceptibility.
The documentation mentions that these tests simulate the drone flying through intense external electromagnetic fields, and they specifically highlight the threat of high-power microwave or HPM weapons.
Yes. In modern conflict zones, or even in highly secure industrial areas facing corporate espionage, adversaries don't always try to shoot a drone down with a bullet. They use directed energy.
Like literally shooting invisible waves at it.
Yeah, they will intentionally try to fry the drone's unshielded electronics by hitting it with a concentrated beam of microwave energy. The RS-103 test blasts the drone with intense radiated electromagnetic fields inside an anechoic chamber.
And I imagine the pass-fail criteria is pretty strict.
The standard requires absolute perfection during this test. The signals from the flight controller to the ESCs cannot be interrupted, the telemetry link must remain stable, and the motors must not suffer any momentary loss of control. The drone cannot even flinch while being hit by a weaponized microwave beam.
So, expanding on that whisper analogy, You are desperately trying to hear the GPS whisper while using heavy shielding to silence the air horn of your own motors.
Right.
And simultaneously, you are trying to fly a straight line while someone is actively shining a blinding, military-grade laser pointer directly into your eyes.
That is the grim reality of the electronic battlefield. To survive that, engineers rely heavily on advanced materials. Effective EMI shielding is non-negotiable.
You can't just put the electronics in a standard plastic box then.
Definitely not. The sourcing mentioned the use of specialized conductive elastomers.
I saw that term. What exactly is a conductive elastomer? It sounds like an oxymoron, like
Yeah.
conductive rubber.
That is exactly what it is. It is a highly engineered rubber or silicone material that has been thoroughly infused with microscopic particles of silver, nickel, or carbon.
Oh, so the rubber itself conducts electricity.
Yes. Engineers use these elastomers to create the gaskets that seal the avionics bay. This serves a dual purpose. First, as we discussed in the 810H section, the rubber keeps out the tropical rain and the corrosive jet fuel.
And the second purpose?
Because it is loaded with metal particles, it creates a continuous, unbroken Faraday cage around the sensitive microchips. A good conductive elastomer gasket can provide over 120 decibels of shielding effectiveness against incoming microwave energy, bouncing the attack away from the brain.
That is brilliant. And just to add one final layer of invisible anxiety to the mix, the 461G standard includes test CS117, indirect lightning.
Lightning is the ultimate electromagnetic threat. Now, a direct lightning strike will vaporize a small drone. There's no engineering around that.
Yeah, it's just gone.
But an indirect strike lightning hitting the ground or another aircraft nearby generates a massive, sudden electromagnetic pulse.
So test CS117 injects lightning-like electrical transients directly into the drone's external cables.
Exactly. It ensures that the massive magnetic field from a nearby strike won't induce a lethal current in the drone's wiring that travels inward and fries the avionics.
It is a relentless, exhausting barrage of invisible threats. And this brings up a crucial pivot in our sources.
The shift to commercial safety.
Right. Dealing with these external threats, ensuring that drones aren't just durable for their own sake, but that they won't unpredictably fall out of the sky when they fly past a cell tower, is why international standards bodies have aggressively stepped in.
It's no longer just about a military contractor wanting a tough drone. It is about commercial airspace safety.
Which leads us to the incredibly strict NATO airworthiness requirements.
We are talking about STANAG, the standardization agreements drafted by NATO. Specifically, the documents STANAG 4671 and STANAG 4703.
This represents a massive shift in scale. Yeah.
Oh, absolutely. We are moving from testing individual components, like shaking a motor mount, to mathematically evaluating the entire system's holistic integrity and legally certifying its right to share the sky with human beings.
Let's clearly define the scope of these two documents because they cover very different machines. STANAG 4671 applies to massive fixed-wing military drones, aircraft weighing anywhere from 150 kilograms all the way up to 20,000 kilograms.
We're talking about machines the size of a private jet.
But STANAG 4703 is where it gets highly relevant to the modern drone industry. It applies to light UAS, drones under 150 kilograms. But there is a very specific chilling metric attached to that weight class.
The kinetic energy threshold.
Right. The standard applies if the drone has a kinetic impact energy of over 66 joules. Why did NATO choose exactly 66 joules?
It is a sobering number because it comes directly from biomechanical blunt trauma studies.
Meaning studies on what happens when things hit humans.
Sadly, yes. If you calculate the kinetic energy of a falling object using its mass and velocity, 66 joules is generally accepted by aviation authorities as the threshold above which that object is highly likely to cause a fatal injury if it strikes an unprotected human head on the ground.
Wow. So NATO's drawing a hard line in the sand.
They are saying it doesn't matter if your drone is a massive Predator aircraft or a heavy-duty commercial quadcopter used for mapping. If it is heavy enough and flies high enough to generate 66 joules of energy when it falls, it is legally capable of killing a bystander.
Therefore, it must be held to an airworthiness standard equivalent to manned aircraft.
Exactly. And the ultimate goal of adhering to these STANAG documents is to earn the right to operate in what the industry calls non-segregated airspace.
Non-segregated airspace. What does that mean for the drone?
Well, historically, drones have been confined to restricted military ranges or very specific, cordoned-off operational boxes. Non-segregated airspace means the drone is legally cleared to share the exact same sky as Boeing 747 passenger jets, local medical evacuation helicopters, and general aviation Cessnas.
You are flying in the public commons.
Exactly. And to be trusted in that environment, you have to prove mathematically that your machine practically cannot fail.
The sources outline how they prove this using two very dense analytical methods: fault tree analysis, or FTA, and mean time between failures, MTBF. How do you mathematically prove a drone is safe?
Let's start with fault tree analysis. FTA is a top-down deductive logical framework. The engineers literally start at the top with the ultimate nightmare scenario.
Like, drone suffers total power loss and crashes into a populated urban center.
Right. Then they work backward, branching out like a tree, identifying every single component failure that could possibly lead to that outcome. They evaluate the main battery, the power distribution board, the individual copper traces, the software logic controlling the power flow.
They just break it down to the smallest pieces.
Yes, and they assign a mathematical probability of failure to every single screw, wire, and line of code. Meantime, between failures, MTBF is what fuels that analysis.
And where do they get the MTBF data?
Engineers use all the data gathered during all the brutal thermal and vibration testing we discussed earlier to calculate the exact statistical lifespan of a component. They must prove that the MTBF of critical systems far exceeds the actual duration of the drone's mission by several orders of magnitude.
It's an exhaustive, incredibly tedious mathematical proof of safety. Every single component must justify its existence.
It's tedious, but it's the only way to guarantee safety.
But while reading through the NATO certification requirements, I found one physical test that genuinely surprised me. We've talked about lightning strikes and microwave weapons, but STANAG focuses massive attention on a much more mundane, everyday threat.
I know exactly the one you mean.
I'm talking about CS-118, personnel-borne electrostatic discharge.
ESD. A simple static shock.
The standard strictly dictates that the drone must withstand a 15 kilovolt static shock. That is 15,000 volts.
It sounds like a lot, and it is.
And the simulation they run isn't a lightning bolt. It is literally just mimicking a technician or an armorer walking up and touching the drone with their bare hand.
Everyone has experienced this. Think about a cold, dry winter day. You walk across a carpeted floor wearing socks. You reach out to touch a metal doorknob and zap. You get a painful little shock.
Right, we've all done that.
That tiny spark you feel can easily be 5, 8, or even 10,000 volts of electricity. Now, scale that up. Imagine a military technician working in a hyper-arid desert environment, wearing synthetic, moisture-wicking combat clothing, walking across a tarmac to load a sensor payload onto the drone.
Their body is just acting as a massive capacitor, building up an immense static charge.
And then they reach out and touch the carbon fiber chassis.
The instant they touch the drone, they discharge 15,000 volts of static electricity directly into the airframe.
Electricity is lazy. It always seeks the path of least resistance to ground. If the drone's internal electrical architecture isn't brilliantly engineered, that 15,000-volt surge will travel right through the chassis, bypass the shielding, and blast straight into the delicate 3-volt semiconductor chips inside the main flight controller.
A completely ordinary static shock from a human hand can instantly execute a multi-million-dollar piece of hardware.
It can cause microscopic dielectric breakdown inside the silicon chip, permanently destroying it. Or, more insidiously, it can cause the flight controller's software to instantly reboot.
And if the drone is sitting on the runway, a reboot is an annoyance. But what if it's already flying?
Exactly. If that technician touches the drone right before a hand launch, and the drone reboots while it's being thrown into the air, it becomes a 66-joule projectile. The CS-118 test ensures that the drone's chassis and internal grounding architecture are designed to safely absorb that massive 15-kilo hit, route the energy entirely around the sensitive electronics, and dissipate it safely.
All without the drone's brain ever even noticing the surge happened.
It is a stunning testament to how fragile the internal logic of these machines is, and how robust the external engineering must be to protect them from something as innocent as us.
But here is the hard, uncomfortable truth that all engineers eventually have to face. Despite the virtual danger room simulations, despite freezing it in a vacuum, shaking it to the point of resonance, shielding it from microwaves, and proving its math to NATO, machines are machines.
Entropy always wins eventually.
Right. A bird strike shatters a propeller. A hidden manufacturing defect in a battery cell causes a fire. So the ultimate question is, what happens when the drone experiences a catastrophic, completely unrecoverable failure in midair?
When it stops being a drone and becomes a rock.
Exactly. What happens when the brain dies and it reverts to being a falling brick?
This is where we cross the threshold from proactive engineering to reactive mitigation. We enter the realm of the last resort, fail-safes and safety termination.
Our sources dedicate significant space to this, specifically focusing on the FTS, the Flight Termination System. This is the ultimate pull-the-plug mechanism.
And the most fascinating and crucial detail about the FTS is the requirement that it must be a completely independent, standalone system, utterly decoupled from the drone's main flight controller and the main power battery.
Why is that separation so important?
It's an incredibly important architectural distinction. You have to ask yourself, if the main flight controller is the smartest, most capable piece of silicon on the aircraft, why on earth would you take the most critical safety decision out of its hands?
Oh, because of catastrophic failure.
Yes. If the drone suffers a massive power bus short circuit, or if the main lithium battery erupts in a thermal runaway fire, the main flight controller is instantly dead. If your ultimate safety parachute relies on a dead computer to tell it when to deploy, you do not have a safety system. You have a false sense of security.
It operates precisely like a dead man's switch.
Exactly. The FTS is its own little world. It has its own very simple, ultra-reliable microcontroller, and it has its own dedicated fireproof backup battery.
And what is it doing while the drone flies?
It sits there during the flight, quietly monitoring a constant heartbeat signal from the main controller. Or it listens for a dedicated, encrypted kill command from a secondary radio link operated by the pilot.
And if that heartbeat stalks?
If the drone goes rogue, a scenario they call a flyaway, where the navigation goes haywire, or if it loses all communication links, or if that heartbeat stops, the FTS wakes up and violently takes over. It initiates a lockdown.
And the speed of this lockdown is terrifying. The testing requirements dictate that within 50 milliseconds of detecting the failure, the FTS must physically cut fuel lines or sever the power to the electric motors, stopping the propellers dead.
50 milliseconds. It's barely a flicker in time. It doesn't ask the main computer for permission to shut down. It initiates an immediate, hard, physical kill of the entire propulsion system.
But cutting the motors just ensures the drone starts falling faster. That's where the second half of the fail-safe equation kicks in. The ASTM F3322 parachute standard.
Right, the parachute deployment.
The document dictates that once the propellers are confirmed dead, a ballistic parachute must deploy in just 200 milliseconds.
The speed is critical because a drone in free fall accelerates at 9.8 meters per second squared. You have very little altitude to work with.
The parachute shoots out of a tube, usually propelled by a small explosive pyrotechnic cartridge or a massively compressed spring, right?
Yes, it's forceful deployment.
And the standard requires that this parachute must limit the drone's terminal descent velocity to under 4.5 meters per second before it hits the Earth.
That 4.5 meters per second number is carefully chosen. It is roughly equivalent to the speed a human being reaches when jumping off a low brick wall.
So it's still going to hurt the drone.
Oh, when a 100-kilogram drone hits a pavement at that speed, the internal components will likely shatter. The drone is destroyed. But the kinetic energy is low enough that it shouldn't cause a fatal skull fracture if it happens to land on a pedestrian.
Wait, I have to stop here and ask a vital, fundamental electrical engineering question. You mentioned the FTS has its own independent battery.
Right, it does.
But the FTS is still bolted into the same physical chassis as the main electronics. It still has to communicate with the main brain to monitor that heartbeat.
Okay, I see where you're going.
If the main battery suffers a massive 50,000-volt short circuit, how do they wire the drone so that the deadly voltage spike doesn't just travel down the communication wire and instantly fry the FTS computer before it can even fire the parachute?
I love that you caught that, because that is the most difficult problem in fail-safe design. You have the high-voltage, high-current circuits of the main drone, the massive batteries, the ESCs, and you have the highly sensitive, low-voltage trigger circuits of the FTS, specifically the pyrotechnic triggers that use a tiny spark to fire the explosive parachute cartridge.
Right, so a surge could set it off accidentally.
Exactly. If you connect the main brain to the FTS using a standard copper wire, a voltage surge will travel down that wire at the speed of light. It'll either instantly fry the FTS, or worse, accidentally trigger the explosive charge and blow the parachute out while the drone is flying normally, causing a crash.
So you absolutely cannot connect them with a physical wire. But how on earth do two computers communicate with each other if they aren't physically wired together?
They use a brilliant electrical engineering trick called galvanic isolation. They separate the two electrical domains entirely, and they pass the signal across a physical void using light or magnetic fields.
Like using a flashlight to signal someone across a canyon.
Yes. The most common method uses a tiny component called an optocoupler. Inside this tiny black microchip, there's a microscopic LED connected to the main flight controller's circuit. Directly across from it, separated by a gap of clear, non-conductive resin, is a light sensor connected to the FTS circuit.
Okay, so when the main computer wants to send the heartbeat signal.
It pulses the LED light. The sensor across the gap sees the light and relays the signal to the FTS. There is zero physical electrical connection between the two sides. They are galvanically isolated.
That is incredibly clever. It is literal communication using flashes of light across a microscopic void.
And it solves the short circuit problem perfectly. If a massive 10,000-volt surge destroys the main flight controller, that surge travels down the wire and completely incinerates the tiny LED inside the optocoupler.
But the surge stops there.
Right. Electricity cannot jump across the resin gap. The FTS computer on the other side of the gap survives untouched, realizes the light has stopped flashing, assumes the main brain is dead, and immediately fires the parachute.
That is just brilliant engineering, and it perfectly explains why that sequence timing we mentioned is so ruthless. The FTS has 50 milliseconds to lock down the propellers, and then 200 milliseconds to fire the parachute.
That tight timing is literally a matter of life and death for the parachute system. Think about the physics of a large drone. You have heavy, rigid carbon fiber propellers spinning at up to 8,000 RPM.
Oh, I see where this is going.
If the FTS miscalculates and the pyrotechnic charge fires the Kevlar parachute canopy out of the tube while those propellers are still spinning, those blades will act like an industrial meat slicer.
They will instantly shred the parachute lines to ribbons.
Exactly. In a fraction of a second, the chute is gone, and the drone will plummet to the ground completely unrestrained. The FTS logic must absolutely mathematically guarantee the rotational energy of the props is at zero before the parachute canopy clears the launch tube.
It really hammers home the reality of this entire fail-safe philosophy. This incredibly complex, lightning-fast subsystem has absolutely nothing to do with saving the expensive hardware.
No, the machine is sacrificed the instant the FTS takes over. It is entirely about being a responsible citizen of the airspace and protecting the people below who never consented to a drone flying over their heads in the first place.
It is the ultimate expression of defensive engineering. But having the most brilliant hardware fail-safes in the world, having a drone that survived the virtual matrix and the thermal evans and the NATO math, it still leaves one massive, unpredictable vulnerability in the system.
And that would be the people holding the remote control.
The human element. If you study aviation accident reports, whether it's commercial airlines or military drones, human air fatigue, misjudgment, ignoring warnings causes more catastrophic accidents than almost any mechanical failure.
Which brings us to the final and arguably most important layer of safety: operational procedures.
The sources outline this under ISO 21384-3, which is the international standard governing UAV operational procedures. It covers a massive scope, from how you train your pilots to how you respond to an emergency.
Right, it's very comprehensive.
But there's one specific mechanism highlighted in the engineering reports that represents a fascinating shift in how we handle human operators. It's called the go-no-go checklist, and importantly, it is no longer a physical piece of paper on a clipboard.
Oh no. The days of an aviator walking around their aircraft, kicking the landing gear, visually checking the flaps, and ticking off boxes on a paper clipboard with a pen are completely over for this class of high-end unmanned aviation.
Humans are too fallible to trust with a paper checklist, I guess.
Exactly. The go-no-go checklist has been evolved into an electronic hard gate built directly into the core programming of the ground control station software.
A hard gate, meaning it acts as a physical software barrier. It actively prevents the operator from making a mistake.
Yes. Before the pilot can even arm the motors for takeoff, they are forced to go through this digital checklist. But the pilot isn't just mindlessly clicking yes, yes, yes to get through it. The software itself is actively interrogating the drone.
What kind of things is it interrogating?
For example, the software automatically checks the status of the RTK GPS.
What is RTK?
Real-time kinematic positioning. Standard GPS might give you a position accurate to a few meters. RTK uses a fixed base station on the ground to correct the GPS errors in real time, giving the drone a positional lock accurate to within a single centimeter.
Oh, wow. A single centimeter. That's vital for autonomous precision landing.
Right. So the hardgate software queries the drone. Do we have a solid RTK lock? It varies the communication links to measure the exact level of electromagnetic interference in the area. It verifies the temperature of the batteries. It checks the calibration of the gyroscopes.
So what does the human pilot actually do?
The human pilot is only responsible for physically verifying structural integrity, like making sure the payload is securely latched and acknowledging it in the system. And here is the kicker. If the software does not register 100% mathematical compliance across every single one of those internal parameters,
The operator's locked out. You can push the throttle stick forward all you want. You can hit the arm button repeatedly and absolutely nothing happens. The motors will not spin.
it is a profound psychological safety net, and it addresses a known phenomenon in aviation called get-there-itis.
Get there-itis, like forcing the flight no matter what.
Exactly. Safety in aviation is not a static state. It is a continuous living process. There's an old pilot's adage, no flying sick. It applies to the pilot's physical health, but also to the aircraft's mechanical health. But human beings face immense operational pressure.
Like a commercial drone pilot on a movie set. The director is screaming, daylight is fading, millions of dollars are on the line.
Right. The pilot looks at their screen and sees a minor warning light indicating a slight temperature variance in motor number 3. The human pilot, feeling the pressure, might rationalize it. They might think, it's probably just a sensor glitch. The drone flew fine yesterday. I can push through this and get the shot.
We've all done that in our daily lives.
Yeah.
You see the check engine light come on in your car, you decide the engine sounds fine, and you keep driving to work because you can't be late.
We all rationalize risk when we are stressed. But the electronic hard gate ruthlessly removes that human bias from the equation. It takes the pressure of the decision off the human pilot's shoulders.
It makes the safety decision binary, cold, and immutable. If the machine isn't 100% healthy, it stays on the ground, period.
The director can yell all they want. The machine physically refuses to compromise its own safety standards.
And this adherence to strict procedures doesn't end the moment the drone lands safely. The engineering reports heavily emphasize something called IC, Instructions for Continued Airworthiness.
These are highly detailed, legally binding maintenance logs governing operational limits and replacement cycles.
This is where the entire engineering life cycle loops back on itself, isn't it?
Yes, the ICA documents are directly informed by the brutal MIL STD 810H testing we discussed at the beginning. Remember the sign-on-random vibration tests and the terrifying thermal shock fatigue?
The engineers didn't just do that to see if it broke. They did it to gather incredibly precise mathematical data on when it breaks.
They calculate exactly how many cumulative flight hours a specific aluminum motor mount can endure before the microscopic fatigue cracking reaches a statistically significant level of danger. That hard number goes into the ICA manual.
So if the manual dictates that the carbon fiber propellers and the aluminum mounts must be replaced at exactly 200 flight hours,
It does not matter if they look brand new to the naked eye. At hour 200, you unbolt them and throw them in the trash. It is a proactive maintenance philosophy designed to replace parts before they fail in the sky based on the horrific torture they endured in the laboratory.
So as a listener, what does all of this incredibly dense engineering data mean for you? Why should you care about galvanic isolation, optocouplers, and Gonago software hard gates?
I think the takeaway here is a profound lesson in high reliability operations. You can apply it to almost any complex industry or process in your own life.
We naturally tend to trust our own judgment. We think we can manually manage complex systems. But humans are fundamentally flawed. We get tired, we succumb to external pressure, and our attention wavers.
True, uncompromising reliability comes from building systems that actively remove human bias from the critical safety checks.
Whether you are building a military drone, designing a hospital's surgical safety protocol, or creating a financial auditing process for a massive corporation, it is about having the humility to build a system that actively protects you from your own worst instincts.
It is the pinnacle of defensive engineering. You start with the baseline assumption that everything, the environment, the hardware, the software, and the humans operating it, will eventually fail. And you design a mathematically proven path to safety regardless of those failures.
We have been on a genuinely incredible journey today. We started by plunging a pristine digital twin of a drone into a virtual matrix of fault injection, watching its software brain desperately recalculate its aerodynamics in 100 milliseconds just to stay upright.
We took the physical prototype and suffocated it in a 6,500-meter vacuum to see if its batteries would explode.
We froze it at minus 40 degrees and threw it into an oven at 75 degrees just to try and shear the microscopic solder joints off its circuit boards. We shook it violently on multiple axes to find its resonant frequency.
We zapped it with 15,000 volts of static electricity to simulate a human touching it on a dry day, and we blasted it with military microwave weapons to ensure it wouldn't blind its own GPS while trying to fly.
We learned how an independent secondary computer uses flashes of light across a microscopic void to fire an explosive parachute in 200 milliseconds to save the people on the ground.
Mhm.
And finally, we saw how cold, binary software hard gates prevent stressed, tired humans from making fatal mistakes on the runway.
It is an absolute astonishing gauntlet that these machines must survive just to be deemed safe enough to share our sky.
It represents a monumental achievement of human engineering. But, as with all technology, it is a constantly moving target. And that brings up a really provocative, somewhat unsettling thought when we look at the immediate future of these systems.
You're talking about AI.
Yeah, some of the most recent sources we examined, particularly the tactical reports detailing drone operations in highly contested environments, talk about the rapid accelerating integration of artificial intelligence.
Because traditional signals like GPS and radio control are so easily jammed in modern warfare, engineers are using AI to make the drones fully autonomous.
They are using advanced computer vision to let the drone navigate by visually matching the terrain below it to a digital map without needing satellites. They are even employing AI algorithms for automated target recognition and engagement in the terminal phase of a flight.
So the drone isn't just flying itself, it is actively analyzing what its camera sees, interpreting the environment, and making life or death decisions entirely on its own.
That is the reality we are entering. Now, take everything we just spent the last hour talking about and apply it to that new reality. We know exactly how to use a shaker table to test a carbon fiber strut for vibration fatigue.
We know how to cycle a circuit board in an oven to test for thermal shock.
But how on earth do you test the psychology of an artificial intelligence? If the drone is flying itself and making tactical decisions, who writes the go-no-go checklist?
Will future revisions of MIL STD 810 or NATO STANAG require engineers to digitally inject hallucinations into the AI's visual feed just to see if the neural network makes a fatal error in identifying a target?
How do you mathematically certify the airworthiness and safety of a machine that is constantly learning, evolving, and changing its own decision-making matrix during the flight?
We are rapidly moving from the era of testing physical physics to the era of testing digital cognition. And the standards bodies haven't even begun to figure out how to write those rules.
That is a wild, incredibly complex thought to leave on. Testing the psychology and the morality of an AI drone. It makes you realize that as impossibly rigorous as this hardware gauntlet is, the software testing gauntlet of the future is going to be infinitely more terrifying.
He really is.
Thank you so much for joining us on this deep dive. It is a massive amount of technical engineering to process, but I guarantee you will look up at the sky a little differently next time you hear that high-pitched hum of a drone flying overhead.
You will know exactly the kind of invisible hell it had to survive in the laboratory just to earn the right to be up there.
Keep wondering, keep questioning how the world around you works, and we'll see you next time.